First of all, thank you for the introduction. Today, we together will be giving a presentation on, it's titled Ultrashort and Ultraviolet Laser Pulses. We will be looking at technology and applications. Jean-Philippe Colombier explained who we are, so I just go directly to the slides. And now we are structuring this talk in the following way. At the beginning, I'll make an introduction to lasers to the people who are unfamiliar with the topic. We will be looking at a continuous mode laser until, we will look at interactions between laser and materials. We will see the differences in the interaction when the laser from continuous mode change to ultra fast laser pulses. We will see the differences, and then we will stay in the ultra fast laser mode. In ultra fast laser mode is very often we work on infrared laser wavelength, and then in the section 2, so we will be looking at why we want to talk about ultraviolet. In this section, Nicolas COMPERE will show that advantages that we for what reason we want to use UV or ultraviolet or UV laser pulses, and we have to have a look as well the limitations and the choices of the laser sources, especially when it's concern of industrial applications. And then I'll take the micron back. I would like to share with you in section 3 some different applications, and I categorized the applications in terms of different material families. We talk about laser UV, ultrafast laser pulses, machining of metals, wide bandgap materials, and biological materials. We will have a short conclusion at the end. Okay, so about introduction about lasers from continuous laser mode to ultra-fast laser mode. I break this into 3 sections. Continuous one is the column on the left, and then a long pulsed laser irradiation on the material. This is the column in the middle, and then the column on the right-hand side is the interaction between material and the ultra-short laser pulses. Ultra-short laser pulses or femtosecond laser pulses. I use them interchangeably. Okay, let's start from the column on the left, which is continuous laser irradiation. In this mode, the laser irradiating on the material is quite similar to other sort of heating, like a radiator. As a consequence, the material being irradiated, the temperature of the material rises. At some moments, when the melting temperature is reached, then the material experiences a phase transition. And in this scenario, you have the solid phase transition into liquid. And then if we stop laser heating, then the liquid coming back to solid. And in this transition changes, we can change the geometry, topography, shape of the material. And so in this scenario, the applications can be sought from laser welding, laser joining, laser forming, and things like this. And then if we chop the continuous laser light into pockets, and then we use those pockets to irradiate on the material, then we can, hit the material more efficiently, in a localized fashion. As a consequence, we can irradiate. The heating is only affected in a small area of the material, and in this small volume, where the volume sees the laser light, the temperature rises violently. We can have transitions from solid to liquid, from liquid to vapor, and the formation of the vapor generates shock waves and recoil forces. So this recoil forces pushes the liquid, some solid fragments, atoms, plasmas out of the zone being irradiated, and this is effectively called laser ablation. And with laser ablation, we can remove materials. So in this scenario, applications are laser drilling, laser coating, engraving, marking, and so on. And then if we further shorten the pockets of the laser lights, when we come to ultra-fast regime of the femtools, then we have different laser material interaction. In this scenario, the laser pulses, the femtosecond laser pulses, interact with surface electrons first, and then the laser pulses extinguish, and then it's left the excited electrons to interact with the rest part of the material, with the lattice, through electron-phonon coupling. And in this scenario, we have a minimum negligible thermal effects. So the material experiences some sort of interaction, ablation without significant heating effects. As a consequence, we can use the laser ablation to remove, for example, material from a match head without ignition. And we can do laser drilling on a human hair without bending it, without burning the hair. And they are the examples to show how ultimate precision we can get with ultra-fast laser pulses. And with ultra-fast laser pulses, with ultra-fast laser technology today, it's more than often we work on infrared or IR wavelengths, either 800 nanometers or 1030 nanometers. However, we do have some advantages that we want to use ultraviolet or UV, ultra-fast laser pulses. And now I leave the floor to Nicolas COMPERE to explain why we want to use ultraviolet, ultra-fast laser pulses, what are the advantages and the choice of laser sources. Thank you. Thank you, Nicolas.
Thank you, SEDAO. So yes, in terms of ultra-fast laser process, we are more and more challenged by the research world and by the industry to work with femtosecond laser in UV. Why? Because thanks to this wavelength, we can reduce 3 or 5 times approximately the size of the beam diameter, allowing to design some patterns which are more close to 1 micrometer or less in nanometer scale also. And it can also have a different interaction, metal-laser interaction. Because even if we are in femtosecond laser field, we have some limited thermal effects, and these thermal effects are less present when we go from infrared to UV. So it's also a good point for the UV. We can treat different material because some of them are invisible in infrared. So if we want a good surface absorption, we can go for this range of wavelength also. Higher, the photon have a higher energy, which allow a different process and ionization of the surface. And so for drilling, cutting, some kind of dielectric, for example, it's easier to have to do it in UV. We have better removal rate, and we can also mix different kind of wavelength. So globally, we have a better machining quality, a better precision, and also speaking of the lips, the structure of lips is strongly linked to the wavelength. So if we reduce the wavelength, we also reduce the periodicity of the lips, and this allows some good application like surface developing, also some kind of photon absorption with the light incoming on the surface, and SEDAO will introduce after some kind of application with that. So if here you have some drawing to see the benefit of the UV. So as you can see, even if we are in the femtosecond range, we have good quality comparing to the picosecond, nanosecond of drilling. So you have the example of a hole, but in the femtosecond femtosecond range, we can have better quality and we masterize the type of interaction in the material closer when we go for UV. Also, comparing UV, but in a range of pulse duration of nanosecond and femtosecond, we see also the benefit of the femtosecond range. So this is why we want to work closer to UV, but it's also a challenge to work with UV. And so we have different manner to come to have a UV femtosecond laser pulse. So the lower price system is the homemade system with non-linear crystals. So we experienced to have this kind of crystal, allowing to change the wavelength, and by putting them in cascade, we can reach UV range. So this solution is cheap because it's 1,000 € approximately. But if you can include also the time of the people to make it working properly, because you have to set the laser beam with the good diameter to have the best yield. You have to make good alignment of the crystals, and also to manage it, because depending on the different days, you have every time to realign it to get exactly the same power, the same energy, and it's easy to put the system and to set up, but you have to do it all the time. So it's not something which allows the TRL increase and to do some pre-series for industrial world. Then you have the dedicated subsystem, which is approximately 10,000 €. It allows to have a femtosecond laser source in infrared, and then to transform infrared to wavelength to UV wavelength in a one box system. You can buy it; it's cut on the shelf, and you can integrate it. You have just to have a good alignment between the laser and this system, and then you have a certain amount of power outside. So it's optimized from this component, but and you can put it just on the line, but it's not as flexible because you can't act on different parameters. You have the box, laser beam incoming, the output, and then you have a result. And then the last solution, so it's the higher price solution. You can provide yourself this solution for an amount of 200,000 € and more, depending on the output you want in terms of power and pulse energy. The advantage of this solution is that the laser itself is produced by the manufacturer, and then you have all the laser settings that you can go with to have the good process on the surface. And as all is included, the manufacturer himself is in charge of providing you the best laser beam profile and the capability to change all the settings to have, truly speaking, femtosecond laser UV source. So it's the most expensive, but for pre-industrial process and to provide also to research world a strong tool with capability to change all the parameters, it's a good solution. So it's the one we are just integrating. So just to finish, yes, we go right now for UV 347, but we can go also for fourth order UV. But in this field of UV, we have a problem because the air becomes opaque. So we need to have some system to work under vacuum, which add more complication to the system. But beginning with a third order UV is a beginning.
Okay, thank you. So those first two sections are the facts, and now I just want to share with you a couple of examples, small examples, and we can start with UV ultrafast laser pulses interact with metals. I chose titanium. Titanium, for example, in in biochemical, biological applications. I chose one, titanium. Titanium can be used for lots of different implants, bone screws, bone plates, prosthesis, and I chose just a dental implant to show this example. And dental implants, again, it depends what environments we are looking at. We may want to have different surface functionalities or different surface laser patterning results. If we look on the top at the interface of the tooth and the gum tissue, we would like to have some sort of antibacterial properties so that bacteria, they are not going to accumulate, not going to proliferate on the inside the mouth, close to the tissue. And then if we look a little bit underneath in the gum region, then we want to have pro-adhesive properties to let the gum tissue attach firmly on the surface of the implants. This is to stop if there are any bacteria proliferation on the upper part, then they will not go into the lower part, which is the screw part. Here we have the interface between a jawbone and the implants. And here we want to have some osteogenesis properties so that cells, the bone cells, will adhere, attach, and grow on the dental implants. And the better the osteogenesis property is, the better we have a good chance of a successful implantation. And today is a vast topics of different objectives. And today we are just going to talk about antibacterial properties on the upper part of the implant. And as Nicolas just said previously, with femtosecond laser, we can generate quasi-periodic nanostructures. They call ripples or lips. And these nanoscale structures, their periodicities are very closely related to the laser wavelengths that we use to irradiate the material. With infrared ultra-fast laser pulses, we can generate laser nanostructures, ripples of 600 nanometers periodicity. It turns out as the small SEM image. So on the bottom on the left, this 600 nanometers periodicity is hotbed. It's very comfortable for the bacteria to proliferate, to accumulate, and be active. On the other hand, we can produce nanostructures with UV laser pulses, ultra-fast UV laser pulses, and we create periodicity smaller than the wavelength of the laser source. What we have here, the same image on the bottom right-hand side, we have 200 nanometers periodicity of the nanoripples, and this periodicity, they are smaller than the size of the bacteria, and this being very resistant to attachments of bacteria. And this is still ongoing research. It's called LASIMP, and this is a research project financially supported by Manutech-SLEIGHT. And then a next example on large bandgap materials, and this is because the electronic structures of the material, they are transparent, they are very hard, and electrically insulating. And these materials like silicon carbide, gallium nitride, sapphires, they are very commonly used in microelectronics, light emitting devices. And as we all know, with ever shrinking dimension request that more and more demand for direct laser patterning, not necessarily to be laser, but direct patterning on parts of the devices to realize some functionalities all together with the microelectronics and light emitting devices. These applications are in MEMS, lab on chip, and mobile phones, mobile phone sensors, LEDs, and so on and so forth. In the middle, I put a couple of examples, images to show on the left-hand side, we have UV ultra-fast laser machining. On the right-hand side, infrared ultra-fast laser machining of large bandgap materials. We can see in terms of smoothness or roughness, we have a supreme quality achieved by UV ultrafast laser pulses. And in terms of the edge qualities, the sharpness of the features machined, we again ultrafast UV laser pulses win the quality contest. And then furthermore, there's more things to add. Infrared femtosecond laser machining of transparent large bandgap materials. This requires multi-photon ionization. But when we're machining a small electronic devices, there's a potential that infrared ultrafast laser photons transmit, part of the photons transmit and damage underlying electronic circuits. And UV ultrafast laser pulses, in this case, these photons, UV photons, they are used to do direct bond breaking, and they are opaque to the transparent, opaque to with anti-gimme bond break, opaque transparent materials. It's actually opaque. It hits the surface, and the UV photons stops there. Then, for this reason, we have less collateral and longitudinal damages with UV ultrafast laser pulses. And then we have biological materials such as biocompatible polymers and hydrogels. We have also advantages of deploying UV ultrafast laser pulses. Well, I think I'm a little bit running out of time, so I'm not going into details. We can have a look afterwards if this is interesting to you. I'm just going to closing remarks. Ultrafast laser technology, that's more or less the solid state technology that determines high power, high repetition rates laser pulses, especially used for industrial processing. They are femtoseconds or picoseconds. The wavelength of the laser source is very often in the infrared light. And due to the short duration, pulse duration, and multi-photon ionization, infrared femtosecond or picosecond laser pulses can offer already ultimate high machining precisions and minimum collateral and longitudinal damages. And nevertheless, ultra-short UV pulses still offer unique and sometimes enabling solutions for creating applications when we need smaller sizes, when we need bone and chain cleavage. And as I hope I shared successfully some examples with ripples, with small ripples, and with transparent materials application, machining applications, that we do have sometimes UV, ultrafast, ultra-short pulses being the enabling solutions for us. And as well as Nicolas COMPERE explained, although we have advantages of using UV ultra-short laser pulses, it's very often the fact it's more expensive and technologically there's more complexity and it's quite costly for the maintenance, and there are more facts to be taken into consideration before really we deploy UV ultrafast laser pulses. And I think that's all. Thank you.
Thank you.